You have probably heard it said that using goto is considered one of the worst practices in programming. This is largely true. Why then am I spending an entire lesson teaching this? Well, several reasons. First of all, although it is poor practice in most languages, it is still part of the core functionality built into your CPU chip. In other words, it is fundamental to computing as a whole, and any software written by any programming language uses it. You really do need to understand this concept. Second of all, it will help you to understand future lessons at a deeper level. And lastly, it will help you should you encounter someone else's programming code that uses goto statements. Now, I want to add that you will never need to use a goto statement in C or most programming languages. There are almost always better ways to do whatever it is you're trying to achieve. So, all of that said, let's begin. Now, I have introduced conditional flow statements to you, and I've shown you that it is possible to write a program that can choose to skip over instructions that should not be executed. For example, consider this code. So, what is really happening here? At a machine code level, first of all, a subtraction operation is performed using height and 5. If the result of that subtraction is 0, that means that height is equal to 5, and then the printf statement is executed. However, if the result is anything other than 0, what happens? Well, it's going to jump over the code inside of the if statement. Now, I am sure that you understand this at an abstract level, but how exactly is this done? How is your CPU chip able to jump over programming instructions? Recall from the lesson entitled Programs Are Data Too that a program is data just like anything else, and it is stored in memory. We learned in earlier lessons about the instruction pointer, which is built into the CPU chip, which contains the memory address of the next instruction to execute. Each machine code instruction of any program occupies a set number of bytes, and each programming instruction resides at a specific location in memory. One machine code instruction might take up 2 bytes, while another machine code instruction might take up 4 bytes, and so on. Now, in order to make this lesson even more clear, let's visualize this with real machine code. Now, don't worry about exactly how this works. I just want you to understand that this is not hypothetical. We are looking at actual machine code here, and we're using our 16-byte RAM from earlier lessons in order to understand this better. So what you see here, this is all actual machine code taken from a real program. These are not just random ones and zeros. First of all, notice that machine code looks just like anything else. These bytes could be characters or numbers, but they happen to be machine code. This is memory position 8, and this machine code instruction, which actually occupies 2 bytes in this case, is the next instruction that's going to execute. After it executes, then this instruction, which is also 2 bytes, would execute. Each instruction has its own memory address. Each time your CPU chip is about to execute an instruction, the instruction pointer tells it where in memory that instruction is located. By changing the instruction pointer to point somewhere else instead, that instruction, the instruction located at the memory address you are now pointing at, will be executed instead of the instruction that would have been executed. In other words, the memory address contained in the instruction pointer specifies the memory location of the next machine code instruction to execute, and by changing that memory address, you can change which instruction is going to execute. This means that you can jump over code or jump anywhere you want in a program, forward or backward, by simply changing the instruction pointer to a new memory address where a new instruction happens to be. Imagine, for example, that we start at position 8 in memory, and we start executing instructions one at a time until we get to position 14. Let's suppose that at position 14 the instruction reads, change the instruction pointer so that it's pointing back at memory location 8. What will happen? Well, our instruction will go back to position 8 and execute all of the instructions from 8 to 14. Now for this next example, I'm going to make the assumption that every machine code instruction is exactly 1 byte long. Now that is not really the case, so just keep in mind that this is just for illustrative purposes. So follow this example in your mind. You can execute each instruction from instruction 1 through instruction 6, and then what happens? If this were the pen and paper example in our earlier lesson, you are effectively moving the pen backwards. Therefore, you're going to start all over with instruction 1. So what we're saying here is that at position 8 in memory, there is a programming instruction. That's going to get executed, and then the next, and then the next, all the way to instruction 6. And then here, there is a new machine code instruction that simply says, change the instruction pointer to point to 8 in memory, which is where the first instruction is located. Now, to make this slightly more abstract, let me go ahead and show you a different example. Now here what I've done is I've simply given a name to the memory address at the start of the instructions. So rather than calling it memory position 8, I'm calling it label. And now the final instruction simply says go to label, which means to change the instruction pointer so that it contains the memory address which label corresponds to. Remember, in C as well as any other programming language, you are allowed to give plain English names to things that your computer understands as memory locations or specific data. So here, label, what we call label, your computer is going to know as some location in memory where there are machine code instructions. In machine code, the actual instruction which allows you to change the instruction pointer to point to a different location in memory is simply called jump. And the way you write it, if you're writing assembly languages, is like this, JMP. Now, this example right here, don't try it. Why? Because if you look at this example, you'll notice that it will simply go on forever. It will execute whatever instructions are here, and then it will go back to label, re-execute those instructions, go back to label, and re-execute them, and so on. This has a name. Whenever it happens that the same instructions are executed over and over again forever, we call it an infinite loop. Now, we will talk more about loops in later lessons. So if this is the case, that using goto in order to move to a memory location earlier in your program causes an infinite loop, then why use it at all? The answer is because you can control it. And without it, conditional statements themselves are impossible. Just like we looked at in previous lessons, without the use of a goto statement, you can't have if statements or any other kind of conditional statement because they rely on having the ability to jump over code or jump to specific locations in your program. However, when you are writing a real program, the work involving goto statements is done behind the scenes. Also, instead of setting it to run forever as an infinite loop, you can set it to execute a set number of instructions a set number of times, and we'll talk more about that in a later lesson. So let's summarize this lesson. Fundamentally, what you have learned in this lesson is there are mechanisms that make it possible to jump around inside a program. This is achieved by changing where the instruction pointer is pointing. When you change the instruction pointer, this is called a jump or goto statement. The functionality that makes this possible is built right into your CPU chip. And lastly, generally speaking, you will not need to use goto statements in your programs unless you are writing a program in assembly language, because this is managed for you behind the scenes by whatever programming language you're using. Alright, so that concludes this lesson.